Cool. Well, thanks for coming all. I'm Darin, and this is Moazzam, and we're presenting some research we did alongside a couple more colleagues who couldn't be here today, Oner Erdogan and Ray McCormick. And specifically, we're going to talk about a framework we built and some offensive tradecraft for evading detection using AI and cloud mimicry. And then Moazzam's going to talk about some analysis we did of, how that does expose itself in an environment. So we won't go into detail on detection. That's kind of not the point of this talk, but Moazzam will give you some ideas. All right. So before we get to all of that, how has AI already broken a lot of our defensive methodologies? Well, last year in 2025, we really started seeing a lot of malware families utilizing AI for polymorphism. So if anyone is unfamiliar, polymorphism basically means many forms, right? So not expressing yourself or the same way every time, or not performing the same behaviors every time, right? So that makes things harder to profile. So this is not new to AI. AI itself didn't come out in 2025, obviously. So all of this has been around for a while. But it really took off, I would say, last year. And then around the same time, legitimate agentic tools also kind of took off and proliferated. So you can think of Claude Code, OpenAI's Codex, etc., right? And the intersection of those two trends really accelerated this threat, I would say, because you can use AI for really effective polymorphism, and B, you can use AI to write this kind of malware, right? So let's go into the existing threats in just a little bit more detail, and then I'll get to what we did. All right, so there's a few different approaches that you can utilize AI for in this area. So one would be you can use AI to really trick defensive AI agents, right? And get them to do something, or maybe crucially not do something that helps you in some way, right? So Fruit Shell was an example of that we saw last year. Another thing you can do is you can hijack legitimate AI tools, agentic AI tools, and get them to do malicious things on your behalf, right? So prompt injection, maybe data source poisoning, different approaches. But, getting a legitimate tool to perform illegitimate actions. And then finally, there's what we're talking about and what we started with, but then expanded upon, which was using an LLM API, so a cloud service API for a hosted LLM model, to provide variable instructions on how to perform behaviors, right? So this enables that really sophisticated polymorphic malware approach. So what's the specific real-world example that we saw of this? Well, one of them was LameHug. So this was a sample reported on originally by the Ukrainian Computer Emergency Response Team, or CERT, and it worked pretty much exactly how I was describing. So there was a small implant that itself didn't have any really like defined malicious behaviors embedded in it that ran on a victim's endpoint. And then it talked to Hugging Face and an LLM hosted in Hugging Face and asked it for instructions on how specifically to execute some high-level goals, right? And the LLM provided those commands and sent them back down to the implant, and it executed them. And then, it looped over that process for a while and eventually exfiltrated data out to a separate command and control server, right? So that's pretty much what I was talking about. Now, being, red teamers, researchers sometimes, we were like, well, but it got caught. How could we make it not get caught? And the answer we came to initially was that it got caught by network analysis, right? So the victim environment that this malware was found in was doing baselining of their network traffic, and they knew what you know legitimate services were being used in their environment. And Hugging Face was not one of them, right? And neither was this custom C2 server. So that triggered alarms. IR got involved, blah, blah, blah. I don't know. I wasn't involved in that investigation, but I assume that that's how it go. And I do know from what was published that that's how it got caught, like an NDR doing baselining of networking traffic. So we thought, well, let's try and advance the offensive tradecraft a little bit here and fix that method that, distracted from the stealth. So let's build a AI malware framework, not real malware because we're not actual bad guys, but a red teaming tool that does similar things to what LameHug does to evade EDRs, but then also doesn't get caught, we hoped, by network detections, or at least network anomaly detections. And we know that enterprises typically use at least one, maybe multiple, legitimate cloud providers. So if we could profile which cloud providers they utilize already and then blend in, probably we wouldn't trigger those kinds of network anomaly detections. And then also we know that most teams, defensive teams, don't really inspect what we're calling thinking traffic, but specifically this kind of AI traffic in terms of the actual payloads, right, for various reasons. So we went ahead and did that and tested it out, and that's what we're here talking about. All right, so dynamic AI malware. There's some prerequisites here that a threat actor has to do. You first need to actually create cloud accounts across all the major providers, right? So in our cases, we used Amazon Web Services, Microsoft Azure. Thanks to Microsoft for hosting us today. Google Cloud Platform and Anthropic's public AI API or application programming interface. And we support all of those, but you could support more. For example, if you know that you're testing in a environment that uses Oracle Cloud, you could support that, whatever. And then you need a framework that enumerates what your victim uses legitimately. So that's what we built, part of what we built, and determines what you can blend in with. And then once you have that, you're off to the races, and you can use it for both command and control and exfil. And then you you remove not one, but actually two potential detection opportunities at the same time there. So here's a quick diagram of how this works. It's, if you'll notice, rather similar to the LameHug one, except with a lot more cloud provider options. And, you pick one, or rather, our framework does that for you. So that's the idea. And then we called this framework LLMalJ. One of our collaborators likes funny names for projects, so hopefully you'll enjoy that as well. And yeah, this is pretty much how it works. So it's also a minimal implant without much built-in logic. So, if you throw it in a malware sandbox or try to build a profile of its typical behaviors, well, every time it runs, it'll behave differently. So that's hard to do. But it also does the dynamic mimicry feature we talked about and reaches out to, a wide variety of different cloud providers. And then finally, once it's done that, it operates with a pretty standard, I would say, reasoning loop that my colleague Moazzam is going to tell you about.
So let's dig dive into the architecture. So the main key element in the architecture is this React agent, which is reasoning and acting. The reasoning part is happening at the LLM layer, which Darin had outlined how he selected. And acting is happening at the local tool level, where we have tooling to execute commands and write the credentials that we have identified on the Mac OS. And then we have some tooling that enable us to collect some metrics which we use for driving useful insights, which I'm going to show. So let's see what it actually does. It goes through phase 0, which Darin highlighted, where we are identifying which LLM provider the victim is using. And from here onward, it is trying to enumerate all the credential files on the Mac OS system. So it goes through these steps, and each step is a React cycle, which I'm going to go over in the next slide. But here it is going through these folders, if you will, or the areas where different kinds of credential files are residing. It thoroughly goes through each of them, and the result is all the list where important credential files are residing. On the second phase, it is passed on to the agent, where it gets compressed in a zip file and ready for the phase 4, where it gets exfiltrated. So now let's look into the working of one React loop. Almost everything that happens in our agent is this loop. It is happening, and all it is doing is 2 steps. One is the reasoning. With the help of the LLM, it asks LLM what to do, and then executing those steps. And whatever the finding is, it is fed back into the LLM for asking the next action to take. So let's say we are doing this cycle for the enumeration. The question that the agent asks with the LLM is, what credentials exist? And LLM does its own reasoning and provides you that you should check this .ssh folder first. And the agent uses its tools to take action and run this command in order to find what is in this folder. And as a result, we find these files in that folder. The agent may decide that it wants to continue, and if it does not, then the result is passed on to the next phase. If it does want to explore more, it runs in a cycle. The important point that I want you to take from this slide is that even though LLM, we don't know how it is thinking, how it is coming to this conclusion, we do have a very distinct footprint or fingerprint specific to this architecture, because it is it is making a continuous call to the LLM agent, and then it is executing some tools on the endpoint itself. So keep that in mind, because it's going to help you in the next slide, because that's give us a signature that we can fingerprint that thinking process of these agents. So let's go over some of the insights we gathered from the telemetry that we are collecting. We did this experiment where we competed this agent with humans and a static script that we had written. The purpose of all three actors was to enumerate and harvest credentials on a Mac machine. Typically, an agent took 18 commands to complete this task, whereas a human took about 12 commands, and the script was constant. We did not use any framework, so that was a constant. It always run those 26 commands. For the second timing signal, that is the interesting part. That's where that signature that I was talking about in the previous slide comes into play. We saw that there was this consistent gap of 2 to 6 seconds between the running of two commands on an agent, whereas this was very different for a human, because we as a human take breaks, we make mistakes, we go Google things or ChatGPT commands and try to research what is the next action we should take. So that was more of a bell curve with high variance. The 10 or 11 minutes of execution time you might find it in strange why agent is taking more than a human, which is about 6 minutes. There is a reason. The instructions that were provided to our test human was very limited, whereas the agent was very thorough, very greedy. It was trying to find every single directory on a MacBook. So that's why it took time, and it has to go talk to the LLM agent. So the latency, network delays were involved. So that's why that time is higher. This recon ratio is also very interesting aspect, because we wanted to see how much time agent is spending in each phase, and it was spending about 5 times that in the recon phase, meaning again, it was very greedy, very aggressive before it actually compressed the files themselves. The Jacquard similarity is an interesting one, because it highlights the polymorphic nature of our agent. If you are not familiar with Jacquard similarity, consider two circles. If they completely overlap each other, then the Jacquard would be a score of 1. If they are separate, then it would be an ideal 0. So a score which is close to 0 indicate that within 2 runs of our agent, we did not find any similarities, which indicates that we cannot generate any signatures for detecting this agent. The last one, 46% of recovery rate, is when an LLM made a mistake, did it recover? We are only calculating or measuring the next command that it ran after a failure. We are not measuring the entire process. So the enumeration and harvesting process may have succeeded like in the 4th or 5th run, but the immediate failures were recovered 46% of the time. With these insights, let's see how our defenders can fight this attack. Before I give you some defense mechanism, let's reiterate why this trick even worked. The trick mainly is the attacker is sending the AI traffic to its own tenant, and the tenant level information is invisible to a firewall. The firewall only knows that this traffic is going to this IP, which is a Microsoft IP, and we have whitelisted it. So it just let the traffic which belongs to the attacker as same as your employee's traffic. So that's why we are invisible at the firewall level. On the endpoint, The EDR misses it because it is looking for malicious shell code or some known exploitable pattern, some signatures. And our implant does not have any of that. It is a Python code which is using a standard libraries. It does have an orchestration framework, but that's used by many AI agents. There's nothing malicious there. It is polymorphic in nature, so you cannot create signature because next time it runs, it morphs itself. We saw that with the Jakarta score, which is close to 0. So, and the third most important one, why the LLM is cooperating in the first place. Because if you ask an LLM, okay, provide me instructions to exfiltrate data from .ssh to my server, it would simply refuse. But if you break it down into smaller steps and ask it that way, then it provides you the answer to each of those steps. Because it does not have any memory, it does not know the intent that the agent has in mind. And so each step is benign, but the entire chain is what makes the attack possible. So with these three things in mind, the attack is possible, and that means if you can block these, your attack would be blocked. So that's the motivation. So if you look at this attack, you notice that your EDR is not able to detect anything because there is no binary to scan. There are no signatures. The firewall is obviously whitelisting your traffic because it is going to a known cloud provider that you allow. The NDR is also blind because the traffic is encrypted. So the connection is established and you have a C2 channel established. We are making some assumption. Obviously, we are assuming that your organization is not doing TLS inspection, because if you are doing it and you are validating that the traffic is going to your tenant, then this would be blocked. So let me stop here and ask you guys, are you guys doing that in your organization, like doing TLS decryption and then validating if the traffic is going to your account? Oh, only two. Okay. So that means this is something to look into and validate. Another way to validate that is actually, I'm going to explain that in this slide. So notice that how eager this agent was. It was trying to look into every single directory, and it was very aggressive, which means you can deploy canary flag. Okay. Okay, I will just go quickly and give you the best defense. If you inspect traffic and ensure that your traffic is going to your tenant, or use an AI proxy, then this would definitely kill this attack. And so I recommend that. Where this field is headed, we are seeing multi-agent coordination in the attacker side. We are using an embedded model. When you bring the models to your machine, then that signal or signature that we saw on the network just disappear. Then there is cross-platform mimicry, and then the prompt injection for lateral movement, which means you don't need such a plant. You can use existing AI tool and inject them. On the defensive side, we are seeing intent detection, like intent firewall, to identify what the LLM is actually trying to achieve. Then there are some baselining effect to identify the normal traffic for your organization, and then there is this movement for zero trust AI. I would leave you with this quote, which accurately identify the root cause of the problem. You cannot identify how your AI is thinking, but we also notice that thought has a signature, and we can look for that thought. With that, I conclude.
Thank you.